Okay, thank you very much. Also, I want to mention that today we have two presenters. My co-presenter is David Chao, and now he's the doctoral student at UMD. And so we work together quite often. Okay, the project title is a large-scale assessment by data visualization and rapid data mining. Okay, so what is that? Well, okay, let me move. Okay, so now we have AI, right? Machine learning. Wow, okay, great. However, you know, when you are in a sunny day, you always see a dark shadow. What does it mean? Well, there are some drawbacks, limitation. Some people say, well, uh, when you use traditional statistics, then people do it in a mechanical way. P-hacking, p-value, okay, look for 0.05, cut off, and so on. And people input some numbers into the computer, and hopefully something great may turn out 0.05, 0.05, without thinking, without carefully checking the data structure, the assumption, and so on. But today, when we have data mining, data science, AI, machine learning, then in some way, in some sense, people may go back to the the old habit. In theory, when you mine data, you are doing data exploration. Data mining should be a further step of EDA, data exploration. You want to find the pattern. You want to amend the problem that people they conduct analysis without thinking, hand over judgment to algorithm, to computer. You want to amend this problem by exploring the data in theory. However, now it's too easy. Just push a button, okay, and then people, not all, but some people hand over their judgment to AI. For example, so by far the most powerful predictive modeling is neural network. Wow. So, you want the best fit, you want the best model. Nothing can be more powerful than AI. And the problem is, there are several layers. Okay, input layer, hidden layer. What is happening inside the input? The hidden is a black box. You don't know what's happening. All the transformation, computation, conversion, and so on is done automatically without your involvement. When you go for deep learning, then you have multiple hidden layers. You have no idea of what is happening inside. And then people present output, they have no idea. Well, so my question is, are we going in a big circle? So we want to do data to repair, to amend the problem of p-hacking without human, careful human judgment. But now, are we having the same tendency? Okay, so now let's look at some example. Okay, so today the objective is I will do not really a demo, a screenshot. So it takes too long to do a live demo. A walkthrough, a simple illustration of rapid predictive modeling, RPM. Everything is automatic. AI machine learning will take care of that. And then we want to go back, to data visualization, the old way, manual exploration, human judgment, to understand the data structure in order to determine whether the automatic predictive modeling is appropriate, okay, or which one should be selected, okay. And we will do a triangulation, rather than just let the machine make the decision. We manually run ensemble method and perform model comparison. Okay, so now let's look at the project itself. Okay, large-scale assessment. Okay, a large-scale international cross-cultural assessment by OECD. OECD stands for Organization of Economic Development. Oh, you know what? I missed one word. Should be Organization for Economic and Collaboration Development. Okay, well, you know, I read it, I reread the PowerPoint over and over, but still, well, there are some human errors. Okay, so, and we use the latest information. Okay, the latest one is 2018. This one is a international test. The test is taken in more than 80 countries worldwide every 3 years. OECD tests 3 domains: reading, mathematics, and science. So, for policymaker, for educator to know where the students stand, and also, what policy, what improvement can be done about that. They also collect background information of the student, demographic, teacher information, school information, well-being. Why? Well, knowing the test score alone is not enough, but we want to know why. Why some countries can perform better, why some students need improvement or have room for improvement. So, they collect almost everything and attempt to find out what factors can predict test performance, skill, and knowledge. Okay, so in this project, we don't want to look at everything. Okay, so we only want to focus in the psychological aspect, well-being, how well-being can predict math and science test performance. Okay, so what's well-being? Well, so according to OECD, there are at least 3 dimensions: individual, yourself, your self-image, your health, and also, your motivation and so on. And also the school environment, social aspect, social connection, your friends, your classmates. Out of school environment, once again, social connection, material condition, your parents, SES, do they provide you sufficient resources to excel, and so on. Okay, so now, let's look at how can we do automatic rapid predictive modeling. Today, quite a few software packages provide this option. SAS is one of the examples. SAS is one of the leading DS software, and 2 ways to access our RPM, Rapid Predictive Modeling. You can do it in SAS on in a SAS online, SAS on demand, online server-based computing. When you have big data, it's better not to to burn out your CPU. Okay, or you can do it in SAS Enterprise Guide. Well, this one you can do it on server, on cloud computing, or do it in your local computer. Today our illustration is based upon SAS Enterprise Guide, and as mentioned before, this is automatic, just one click once. So you open the data set, student performance and survey item in all countries. So they OECD collect about 5,000 observation, 5,000 students in every country. What you need to do is that just go to the pull-down menu, data mining, rapid predictive modeler. That's all. That's all. So it's a piece of cake. Okay, now the next step is that you specify which one is the dependent outcome of So in this example, we use a science test performance, and then the rest. How's your health? I like my look, image, right? I like my body, blah, blah, and so on. All this about like well-being related predictor. Okay, the next step is that we advanced analysts. So we, of course, we choose the best. Okay, when you choose a basic, what you will see is nothing more than traditional simple method like OLS regression, and you don't want to do this with like big data. So when you choose advanced, both traditional statistic like regression and modern DS method, neural network, uh, uh, backing, boosting, ensemble methods, and so on will be included. Okay, so now and also we want to do a model comparison when the rapid predictive modeling run multiple methods. You want to know which one is the best, right? So or the champion. So we want to select model comparison. Now the output is like this. The output will be in both web page format and PDF format. Today, this is quite common for people to share the, to share the results on the internet. Okay, for collaboration and so on, and also in PDF. And so uh, the the output is done. People cannot alter the PDF. Okay, in both format, web page and PDF. Now, okay, let's look at what did RPM do. Okay, look at the table on my left hand side. Neural network, ensemble champion, main effect regression. Wow, okay, old school, right? Forward means you run the regression model, start with a no model, and then you add each predictor one by one. In this survey, the OECD survey, there are 119, I think it's 190 plus items related to well-being, which means, the program start with like a one factor model, two variable model, 3, 4, 5, 6, and so forward. Okay, keep going. So, but it's important to point out that I did not choose this method. Rather, the program, the algorithm, make the decision for me. So in this case, what I did is only I go to the pull down menu and then select rapid predictive modeling. That's all, and then I will tell my boss, oh, it took me 4 hours to do that. just one step. Okay, so now you can see the upper two are modern DS method, neural network, state of the art. Also, ensemble champion, random forest, gradient tree, and so on. But the lower two are nothing more than traditional method, right? Okay, so when you look at the output, training, validation in terms of average square error. So how far are the prediction? So how far the prediction away from actual? And you can see the worst. The worst is okay. And then the second worst is main effect regression. And the best is a neural network, right? So, and when you go further, you can see actually the algorithm look at more than one fit criteria. So like AI, here are all the you may say model goodness criteria, maximum absolute error, average square error, AIC, BIC, and root average square error, and so on. And there are a lot of information, but you can see the best is the neural network. Okay, so in terms of least error, wow, okay, we are done, right? So just one step, and then the computer, the machine learning, take care of all the rest. Oh, we are done. Let's go home. Okay, yeah, let's end here. Go home. Well, not yet. Okay, you know, this so-called gas model, we should question that. We pay high price for this best model. Why do I say that? Okay, look at the output. Okay, these are all the so-called important, significant, crucial predictors suggested by the best model. Okay, how many? 1, 2, 3, 4, 5, 6. Oh, wow, you know what this is about? Like, okay, the 25. Okay, so neural network is well fit to the data and achieve high predictive accuracy, but the end result is complicated. So I want to ask you guys a question. If you are a professor, if some student, if someone come to you and say, Professor, what should I do to improve my grade? How can I improve my scientific knowledge? Okay, there are 25 things you can do. 1, 2, 3, 4, 5, 6, 8, and so on. Do all these 25 things, and then you will improve your grade. Well, do you think the student will be happier to hear that? No, right? Yeah. Or if you are a or if you are in a position to make a policy. So this model cannot help you at all, because even if you have resources at hand, it's difficult to do so many things to figure out, okay, how can I make education better? And we have a term for that. These items are not actionable, right? You want only like let's say 4 or 5. Okay, only a few actionable items that you can do something, you can manage. Okay, so now okay, where's my cursor? Oh, what? Okay, here. Yeah. Okay, now let's turn to data visualization. Okay, there are 199 items in the well-being survey, and well, before that, I did nothing. I did not look at these items, and I prematurely submit everything, hand over everything to machine, to rapid modeling. So now I look at this one. Okay, for example, like, oh, I like my look just the way it is. I consider myself attractive. Okay, so these are body image. It's very tempting to collapse items into a few using like a Paxoli square or PCA and so on. After all, they are all conceptually related. You can lump them together under the umbrella term well-being, right? Okay, so how about we just group all response on the left into body image. Indeed, OECD did that. It's called weighted likelihood estimate. Oh, so good. Okay, wow. Okay, the problem is when you really look at the data, then well, in a big data, you always see this problem, overplotting. Too many data. You see, you see everything everywhere. So when you fit the regression line, then p-value, yes, less than 0.001 and so on. And however, Well, there are two problems. First is regression assume a linear relationship. When you have like when you have a big cloud, a big mess like this, how can you be so sure this is a linear relationship? All the points are jammed together. And also you can see actually these points are too far away from the regression line. The residual are too high. So this is not the way. So one way, is less is more. And I use a package from SAS. Okay, it's called a Jumpo. And so I just they have some binning algorithm, binning formula. And when you invoke the feature binning, then it will reclassify the continuous number into certain intervals, like this one called binning. Okay, and then after binning, okay, now I use the binned data to predict science performance. Let's say, okay, body image. Okay, now I can see, when I use the box plot. So when I summarize each bin using the median, I can see a nonlinear trend. So when body image improve from the lowest to a bit better, I can see science test performance improve. But afterward, it just goes south. So when the self-image is too good, like here, then it's worse than low self-image. Okay, so and when I look at all other, okay, I look at individual, I see the same pattern. Okay, it's a nonlinear relationship. Okay, and however, OECD PISA dataset, okay, does not have weighted weighted likelihood estimate for all well-being constructs. So rather than running PCA and then do binning on all of them, it's better to use the data as is. Okay, and however, we learned the lesson. So it's better not to submit our human judgment to AI and machine learning or automatic rapid modeling. Rather, we use backing and boosting manually. Okay. Okay. So okay. I think from this point on, okay, David, can you take
Yes,
over?
definitely. All right. So thank you so much, Dr. Yu, for giving us such a nice overview and introduction to this topic. So here we are going to go through a specific example of how to apply machine learning and big data to a research question, which is how does student well-being contribute to academic achievement indices such as math and science scores? So we first begin with bagging. And so to summarize, bagging is an ensemble or combination of multiple decision tree obtained from repeated sampling. So just like bootstrapping with replacement from one large data set. Then the multitude of obtained results are then combined to form a converged conclusion. Next slide, please. Oh, Dr. Yu, I think you have to
Okay.
go next.
Next, yeah.
Here you go. So as you all can see here, the results are pretty complicated. Many variables are showing to be predictors to academic achievement scores, which is a lot more variables than its boosting counterpart. Next slide. So, and here are the other slides for math scores. So just like the science score slides previously, there are a lot of variables that's shown to be predictors. Next. So now we shift towards boosting or gradient boosted tree, sequential method. So first, the machine learning algorithm will assign all observations the equal statistical weight before producing a model. If that model fails to classify some of our observations, then the misclassified observations will be assigned a heavier weight so that they are more likely to be selected and classified in the next model in the sequence. So lastly, so therefore, each model is then revised and repackaged concurrently until all of the observations are classified. Next. So in this case, you all can see only 3 PISA well-being variables shown to be significant predictors to math score achievement compared to many of the slides in bagging. So next. So same with math. So same with math scores here. And there are only 3 variables that are shown to be predictors when we use the gradient boosted tree method. All right, let's go to the next slide. So now we are going to compare which model is better, bagging or boosting. So we turn to model comparison. Model comparison provides us with the RASE, which is the root mean square error, which is standard deviation of residual values that measures prediction error. The less the RASE score, the better. So as you all can see here, the bootstrap forest or bagging is the winner here. Next. There we go. So one other major advantage is that after we find the predictors, we can perform median smoothing, as Dr. Yu mentioned earlier, to detect trends. So for example, on the first part of the slide, how easy is it for you to talk to the following people about things that really bother you, your teachers, 1 being the easiest, and 4 being the hardest. So thus, it makes theoretical sense that students who have easy access to communicating with teachers score better on math scores. So as shown there's a clear trend here. On the second graph, it shows then the variable, how did you feel the last time you spent time outside of home with your friends bored? 1 is the least bored and 4 is the most bored. So thus, the less bored you are with your friends outside home, the more likely you'll do better. Because being less bored with peers signifies social belongingness and peer engagement, and plenty of research in the past demonstrated this trend as well, that social belongingness and peer engagement leads to academic achievement. So, so now that we had a demonstration on the machine learning method with bagging and boosting on an actual research question, Dr. Yu will lead us with the final discussion and conclusion.
Okay, so what did we learn from this lesson? Well, automatic rapid predictive modeling is quick, but it tends to produce a model that is too complicated. So when you want to get action item, maybe it's not the way to go. It's not practical. And also, you can see, actually automatic or automate rapid predictive modeling include both traditional OLS regression, least square regression. And in my opinion, actually it's not necessary because in our experience, it's not the only project that we have done. I have done quite a few, and time after time, regression modeling isn't good. All the new method, neural network, ensemble, backing, boost, and so on. And always the new method outperform traditional OLS regression. So then you may say, okay, why did the programmer include this into the package? I guess this is just because and some people still want to look at the traditional output. When we submit our paper to a journal, usually the reviewer say, okay, I want to see regression. Okay, so it's only for comparison. Okay, so then some as mentioned before, some people would like to look at the result of regression, and it's only for comparison in our opinion, to convince people that, well, there's something better. The ensemble method is look, okay. Well, okay, just like when you shop for a car, right? Usually the car salesman will show you a lousy car and then will show you a better car. Okay. However, if you really want to do regression, you really want to put something down more in alignment with the traditional method, I suggest use a generalized regression, also known as penalized regression. Okay, what is that? Well, so in the traditional OLS regression, when you want to control overfitting, you don't have much, to do so. When you input more and more predictors, the R square will go up regardless, which means, well, the end result, that result may be too good to be true. So when you have big data, when you have like 10,000 or a million observation, then automatically, almost, without doubt, the p-value will be less than 0.05. Okay, when you have big data, when you enter many, like 40, 50, 190 potential predictors into OLS regression, because this method, has no built-in feature to control overfitting. Okay, but another problem is, well, in the traditional OLS regression, when you have, let's say, 199 plus potential predictors, I'm sure some of them will be intercorrelated, right? Like, all the statement about cell image. Okay, so when you have interrelated or so-called collinear predictors, then you will get to the problem of variance inflation. The variance will be inflated. The model will be unstable. In traditional regression, we have no effective way, well, there are some way, but, not as effective as the new way. So it's not very good at dealing with collinear predictor, and also tend to overfit when you have big data, when you have 199 potential predictors, then bingo, you can, okay, p-value 0.05. However, when you use high regression or so-called penalized regression, then you can amend this problem by imposing a penalty when the model becomes too complicated. Once again, the key is avoid complexity. You want actionable items. You want to tell people, do this 4 or 5 things, and then you can make improvement rather than 10, 20 to 25 things. Okay, so how can it be achieved? Penalty, and which means, in a traditional OLS, so when you look at the output, and almost every potential predictor has a regression coefficient. But however, when you use this new regression method, then when the potential predictors are unimportant, it will be zero out, zero, nothing. So the key is that the coefficient of unimportant predictor will be left out. Okay, and the way to this is called the elastic net, which combining regularization 1 and 2 in lasso and also ridge regression. And so when it's out, this is out, zero. Okay, then at the end you get a compact model. Okay, okay, so according to rapid predictive modeling, neural network produce the best model, quote unquote the best model. Well, once again, the result is too complicated. And in our manual procedure, so we run a backing, boosting, and so on manually. And the bootstrap outperform gradient boost tree, right? Okay, to remind you, we go back to this result. Okay, so when you look at the model comparison, okay, look like, the random forest outperform gradient boost tree. But however, when you look at the output, okay, so here you have the same problem, complexity, too complicated. So, although this output is not as messy as the output of neural network, but still there's a lot, right? So, however, when you look at this one, 1, 2, 3, you want to improve your math performance, do these three things. So you want to improve your science performance, do these three things. Wow. Okay. So my question is, should we always choose the so-called best model? And if I tell you, to do a lot to improve, then can you do it? The gradient boost tree suggests only three most important predictors. It's helpful to inform policy making and also, to inform you how to teach better, or to inform your student how to earn a better grade. Okay. So we should not blindly follow numeric findings. Okay, we should not like, okay, the number look good, neural network, oh, this error. Yeah, well, we should not look at only model comparison output. Oh, random forest is the best. Rather, we want to look at the pattern. So pattern seeking data visualization is indispensable. We should use visualization before and after. Before we pick a particular method, before running predictive modeling, we should visualize the data, look at the data structure. And when you look at the data, you can see, like in this example, overplotting, right? Yeah, then, okay, yeah. So overplotting obscure you seeing the real pattern. You don't know whether this is linear or non-linear, right? So before, you should do visualization to examine the data structure. And after running the model, now you have the best three. You have the top three most important predictors to science and math performance. Now you want to look at the pattern to determine whether you have a linear or non-linear relationship. Okay, so that's all. Time's up. Exactly 35 minutes. Any questions, comments? Oh, silent. Okay.
So we have few questions from the attendees.
Okay.
If you go to below and see Q&A section.
Okay, Q&A. Okay. Let me go to Q&A. Okay. Okay. How is the interaction effect treated in the event method other than OLS? Explain or how the model putting loyalty on complexity. Okay, so actually there are two questions. The first one is about interaction, and then the second one is about a penalty. Okay, actually both random forest and gradient boost tree are built upon decision tree. So you need to build trees before building a forest, right? So for each individual tree model, for each individual decision tree model, you are able to see the interaction effect. By definition, interaction means the effect or the impact of X on Y is inconsistent when you introduce, let's say A, right? So let's say when A is a high, then when X goes up, Y also goes up. When A is low, then when X goes up, Y go down. So when you introduce another factor, then the association between X and Y is no longer the same. We call that interaction. So when you look at individual decision tree, you can see that rather than you have just one gigantic universal statement, when X go up, Y go up, and so on. In the decision, so you can see the so-called the if logic. If X, let's say A, if A is high and X is low, then Y is high. When A is high and X is low, then Y is medium, and so on. Okay, so when you have so-called interaction, follow this next if logic. When you throw in additional condition, if A is high, if B is low, and if C is a medium, then what is Y? Then you can see the interaction. Okay, the second question is about the penalty. Okay, so okay. There are several ways to impose a penalty. AI, for example, like AIC okay, the BIC stands for Bayesian Information Criterion. And there are several things. They are both AIC and BIC take certain things into account to determine the complexity level, like the sample size, the number of parameters to be estimated. And so when you have more, when the model need to estimate more parameters, then both AIC or BIC number will be higher. Higher is the worst, okay, not better. And you know, in the old way, people use absolute cutoff, but both AIC and BIC are not absolute. Rather, it's a comparison. So let's say you have model 1, model 3, model 4, model 5. Then the best model in terms of simplicity, not complexity, will look at the least, the smaller AIC or BIC. So penalty is take the number of parameters and sample size into account to take away or not to disregard model that have high AIC or BIC. Okay, is there a paper related to this presentation? Okay, now David and I are working on the paper, and we will submit the paper to a peer-reviewed journal later. I'm not clear about rapid data mining. Okay. Okay, I assume your question is unclear. What is rapid data mining? Okay, rapid data mining is rather than you manually, select specific modeling methods. So you can do that. You can do it manually. Like in SAS, you can use a neural network, boosting, backing, support machine, and so on. And then you connect the results to a so-called control point and perform model comparison. So this is manual. But okay, when you do rapid, which means only one step, you open your file. So you open your data set, and then you go to the pull down menu, and then you select rapid data mining. Then all the rest, the algorithm will take care of this. Will pick which modeling methods, and then will present you so-called the best model, the best result. Only one step, without much human involvement. This is so-called rapid data mining or rapid predictive modeling. Okay.
I'm so sorry to interrupt, but I have to inform you that 2 minutes are left.
Oh, is getting less important feature is better than getting many feature. Doesn't that mean that our prediction is not strong when we run the same model on other period or population? Okay, not really, because okay, by default, random forest and also gradient boost tree, they rerun the same procedure over and over. So which means the same big data set will be partitioned into let's say 500 times 500 subset, and then so for the gradient boost tree, and they run the first model. They propose the first model with the first subset, and then make improvement using other subset. Random forest is in parallel, which means and so in some sense, the same study is replicated, and therefore it tends to be stable when you apply this into other population. I repeat, both random forest and gradient boost tree do resampling replication, built-in replication. Therefore, it can be well applied to other population. Okay, do we still use, oh, you know what? I think time's up, right? Okay, okay, you can, yeah, I think the time's up. I'm sorry.
Thank you so much, both of you. We really enjoyed very depth knowledge. We learn about different algorithms. If you guys have few minutes left, or you would like to answer the question, that is just one question, by typing, you are most welcome to do that. And thank you so much again.
Okay.
Thank you so much.
Okay, thank you.